Section 5.6 is split into two parts. In the first part, we're going to take a look at two-dimensional objects known as lamina, and in the second part, we'll take a look at the same calculations involving three dimensions. As mentioned, the term lamina is used to refer to basically a two-dimensional object. Now, it can't be totally two-dimensional because two-dimensional implies there is no thickness whatsoever. Well, there has to be some thickness. It could be, however, like a piece of paper, a piece of aluminum foil, something of negligible thickness. But here I've drawn a region, overlaid it on a coordinate system with X and Y's blocked off. The traditional symbol for density is the Greek letter rho, so we will consider rho, the density, as a function of x and y. So the density of an object depends on the xy location on the object. So we'll go through the explanation using the Riemann sums. As you can see here, we have partitioned both the x and the y, where the area of each individual square is going to be delta x times delta y. Notice doubly subscripted. Likewise, we will do the density in terms of just any small rectangular piece. And so the mass of any individual square is the density of that square times the area of that square. Therefore, we can get the area of that entire region by adding horizontally and vertically. And as we do the limit of that, as both the number of horizontal and vertical rectangles becomes infinite, we have an integral. The density could be a function or just a constant. The dA, of course, has to be something that describes the region. And of course, then we have to match these together, make sure that we get the region taken care of. One physical characteristic of objects that scientists and engineers are interested in is something called the moment. Now, here is the definition of the moment. It's the mass times the distance. In this particular case, we're finding the moment about the x-axis, so it'd be mass times the distance from the x-axis. Here's the distance from the x-axis, and we call that just a y. Now, it may not always be rectangular coordinates that we're interested in, so even though in this particular section we're using y to represent this distance, keep in mind that it is indeed the distance. We may have to have some other way of coming up with that. Now notice when we take the integral for mass, which is this without the y in it, that's the mass. So there's the mass times the distance. So this is the distance we were talking about. And notice how it's inside of the integral. And if we wanted the moment about the y-axis, it would be the mass times the distance from the y-axis. And again, we can refer to that distance by the letter x. We may have to call that something different on occasion, but it's the distance from the y-axis. So notice we take the same mass integral that we started with, insert an x inside the integral to represent the distance, and then perform the double integral. And we can put these calculations together into something which we call center of mass. The x with the line over it, oftentimes called x bar, and the y with the line over it, y bar, is the center of mass. And so notice this is m sub y, which is the moment about the y-axis. It may sound a little weird because we're computing x bar and we're using m sub y. But if you recall, m sub y contains the x. And so x bar involves the x distance, or m sub y. Now these are going to be a little tricky to keep up with in your head, so you might want to print some of this off. I have later on the entire set of formulas that you will need on one screen, or you can stop and print this off if you like. However, those are the formulas that we'll be using in this section for right now. Another useful calculation, and very similar to the first one in terminology as in formula also, is what's called the moment of inertia, or sometimes the second moment. Now notice it's very similar to what we just did. It's the mass times, only this time it's the square of the distance. So notice the inertia about the x-axis is the mass, that's all of this, times the square of the distance from the x-axis. And again, that would be the y. And similarly, the inertia about the y-axis. Let's go through this example so you can see how the calculations work. So, like before, we're going to compute the center of mass simply by finding the area, using our double integral concept, of this region, but including the density in there. So here is our integral. We're going to use the y as our first variable of integration, and we're going to let these go from this y value to this y value. Well, every vertical rectangle you put on here is going to have its bottom on the x-axis, which is y equals 0. It's going to have its top on this parabola, which is y equals 4 minus x squared. So we're going from this y value to this y value. It's very important to get these in the proper order. Now the k is what we're using to represent the constant density, just the letter k. In other words, the density may be a 4 or it may be a 5. But it's a constant, so we'll just use a k for that. That means our answer will also come out with k. Now, I'm not going to take the time to do this by hand, but again, if you know how to set up the integral, you can take as much time as you like evaluating it. If you've got a TI-89, that's not going to be very long whatsoever. So the moment then would be that same integral, but with a y, since we're doing the moment about the x-axis. And so again, we just type that into our 89, or take the time to do the integral by hand. And the last one, the moment about the y-axis, same as the mass. The integral for mass is exactly the same integral, only we've got the x in there. So then our center of mass, using our formulas, would be 0 and 8/5. Does this not look plausible? Since this is a constant density, logic tells me the center of mass should be somewhere on the y-axis. And because of the shape of this, I should also have an idea that it's going to be somewhere lower than the middle, since the top of this is at 4 and it's somewhere lower than the middle. So it all kind of makes sense. I'll show you a couple of variable density problems. Now the calculations, the formulas we're going to be using here are the same formulas that we were just doing. We still have the same region, only this time we're told the density varies as the distance from the x-axis. Now I'm hoping you remember this from college algebra. The density is rho. Varies means equals k. So the density varies as the distance from the x-axis. Well, we just did that. If I were to locate a point out here, the distance from the x-axis is y. So there's our density function. So we're going to do the same integrals that we've been doing. Here's the mass, only now notice there's a y, k times y, for the density. Here's the moment about x. Now we already had a k times y, so when we multiply that by y again, we get the ky squared. And the moment about y, again we had the ky to start with. We put an x in there since we were doing the moment about y. And then just evaluate that integral. So we have the center of mass this time at 0 and 16/7, and notice how that's higher than the center of the object because the density is changing. More dense at the top than it is at the bottom. Very similarly, in this one, we're told that the density varies as the distance from the left side. So our density varies. Now we need to describe the distance from the left side. So what is the distance from the left side? Here's the left side. If we pick any point out here, such as this, we need that distance. If we pick a point out here, we need that distance. Now notice it's from the left side, and the left side being x equals -2. So we need the distance from any point x to -2. Well, it's going to be this horizontal distance. To find a horizontal distance, you take whatever's on the right and subtract whatever's on the left. X minus -2 would be an x plus 2. So there's our formula for mass. We evaluate that. We take the integrand to find the moment about x. We stick a y in there, evaluate that. To find the moment about y, we stick an x in there, evaluate that. And then divide. I'll put that on here for you to see. It's way off in the right corner. In this last one, we're told that the density varies as the distance from the top. So here's the density, varies, and then we need to describe distance from the top. Here's the top. How do we describe a distance to any point down here? Well, just like before, the top is at 4. This point, the y value. So we need to subtract top minus bottom. So here's our integral for mass. We'll evaluate that. We'll insert, for the moment about x, another y in the integrand and evaluate that. And we'll insert an x for the moment about y and integrate that. So here's the center of mass. Now here was our definition for the moment of inertia that we mentioned a little while back. The mass times the square of the distance. Now remember that distance means the distance from the line. So here is how we are going to compute the moment of inertia about the x-axis. We're going to use y squared because the distance from the x-axis is typically y. So that would be the square of the distance. Notice everything else remains the same as the formula for mass. Likewise, the moment of inertia about the y-axis contains an x squared in addition to all the components of the mass. There's one other item that we might need to compute, which is the moment of inertia about the origin. That's pretty straightforward. It's just the sum of the previous two. So here we're given a description for a region that we need to try to put together to come up with an integral that we can evaluate. So let's begin by drawing off our region. Here is the points that they're talking about, 0, 0, 2, 2, and 2, 0. So here we have this triangular region. So in describing this triangular region, we need to sort of make the decision in the beginning. Do we want to use vertical rectangles? Y simple we call this. You take book like type 1. If we do, then when we set up our integral, we'd start with dy. Or do we want to use horizontal rectangles? If we do that, then we would start our integral with dx. Now, I don't know which I picked, so we'll see. So here is the line between the origin and the point 2, 2. And so if we integrate first with respect to y, you can see that's the integral I have over here on the left. So that's this rectangle. If we integrate first with respect to y, you can see the bottom of the rectangle is on y equals 0. And the top of the rectangle is on this blue line. Well, this blue line is y equals x. So we're going from y equals 0 to y equals x. Now, typically we don't put the y's on there, although you'll see some textbooks that do. And then, of course, the x's in our picture are going from 0 to 2. So we get the integral set up. Notice the density that was given in the problem is right there inside the integral. So again, from there, it's just a matter of evaluating that integral. Do it on your TI-89. You could actually do this sort of in stages on the TI-84. Maybe I'll show you that sometime if I remember it. However, I've already done that here. The inertia about the x-axis, remember the inertia about the x-axis needs the square of the distance from the x-axis. If we go from the x-axis to some point in this region, that distance is y. So the square of that distance would be y squared. Now I know that would simplify, but heck with the TI-89, you could just go ahead and type just like that. Here is the inertia about the y-axis. Notice the x squared in the integrand. And so the inertia about the origin would be the sum of those. As promised in the beginning, here are all the formulas together in one spot. I will just make one comment here for future purposes. In the formula for moments moments of inertia. The variables that we're using here represents the distance from the point, like I was showing you in the beginning, to the axis that we're trying to find the moment on. And so if it's a rectangular coordinate system, and if we are doing the x and the y axis, then these quantities will indeed be x and y respectively.